Okay. So I'll finish off our theorem 16.16 by proving Lagrange's four-square theorem using the three lemmas I proved in previous videos. So, okay, let's briefly go over the proof here. So I wrote down all the lemmas here. You guys should definitely go check out the my past videos because I posted all the proofs for lemma 1, lemma 2, and lemma 3. So if you're curious, go ahead. Okay, so let's go over the proof now. So Lagrange's theorem is saying that all natural numbers n can be written as a sum of four integer squares. And here we're gonna say n is an arbitrary natural number. Then we can write n as s squared times m, where s is an integer. S is a real number. S is a natural number, and m is a square-free number. M is a square-free. Yeah. So we proceed with the following claim that m can be written as a sum of four squares. So what we're basically trying to do is, if m can be written as like a sum of four squares, then that will mean n is just equal to sa squared plus sb squared plus sc squared plus sd squared. So our claim will be proven. So it just suffices to prove that m can be written as a sum of four squares. Okay, so now we utilize lemma 1-2. Since m is square free, we can use the fact that we could set k is equal to negative. We're gonna set k equals to -1 here, and apply lemma 1-2, and that would give us that there exists integers a, b such that a squared plus b squared is congruent to -1 in modulo m. And we're going to use these exact integers a, b, and apply lemma 2. So we're given a, b here, and if we directly apply this lemma, there's going to exist integers st, u, v, such that these four conditions are satisfied. And as we know, Lagrange's identity. So Lagrange's identity is basically like kind of an extension of Cauchy's inequality or something. But Lagrange's identity just basically says that a squared plus b squared, c squared plus d squared is just equal to ac plus bd squared plus ad minus bc squared. And we're going to apply that here. So u squared plus v squared is going to be congruent to as plus bt squared plus at minus bs squared. And by applying Lagrange's identity here, you can find that this is equal to a squared plus b squared times s squared plus t squared. But what do we know? We fixed integers a, b such that a squared plus b squared is congruent to -1. So we can write this as minus s squared minus t squared in modulo m. So that implies that m divides u squared plus v squared plus s squared plus t squared, right? But then recall from this that s squared u squared plus u squared plus v squared plus s squared plus t squared is less than root m squared times 4, which is 4m, and this is greater than 0. So since m divides u squared plus v squared plus s squared plus t squared, this means that u squared plus v squared plus s squared plus t squared must be m, 2m, or 3m. If u squared plus v squared plus, let me just call it the sum. If the sum of the four squares is m, then we are done, right? But if it's 2m, we have to 2m or 3m, we can apply lemma 3, and lemma 3 tells us that in whatever case it is, we can always write m as a sum of four squares. So that proves our claim, and hence proves our Lagrange's four-square theorem. Thanks for tuning in, and I hope you guys enjoyed this video.